Good morning. My name is Bhooma. Today I'd like to talk to you about my research project involving the Chinle Formation. The overall goal of this project is to understand the westernmost exposures of the Chinle Formation in southern Nevada and to correlate it with the better documented sections to the east. Next slide, please. Here you see a map of North America as it was in the late Triassic, approximately 215 million years ago. The Chinle Formation is a late Triassic sedimentary depositional system that stretches mostly across the Colorado Plateau, extending eastward into New Mexico and westward into Nevada. When you look closely, you'll notice that the western shoreline was along the present-day Arizona, Nevada, and along the shoreline is the subduction zone, and east of the subduction zone is the Cordilleran volcanic arc. This arc was active from the Permian to the Cretaceous with alternating periods of pulses and lulls. The pulses or the flare-ups were periods of intense volcanic activity because of higher magma addition rates into the subsurface chamber. And the lulls were times when there was less volcanic activity because of lower magma addition rates in the subsurface chamber. Next slide, please. This is a view of the Chinle Formation with multiple depositional layers. Each layer has its own physical properties and composition. These characteristics provide evidence to the changes in climatic conditions, the volcanism, and the tectonic events that were occurring at that time. The late Triassic is known to be a time of tropical climate with multiple river systems flowing across the continent and depositing sediment into the basins. The Chinle Formation has been well studied in northern Arizona and Utah, but the westernmost exposures in southern Nevada have not yet been well studied or isotopically dated. Next slide, please. Again, looking at the map, you see the Chinle Formation across the Colorado Plateau, the Cordilleran Arc, and the orange indicates the approximate location of our sample collection. The Cordilleran Arc was active in the late we mentioned that it was active from the Permian to the Cretaceous. The late Triassic, when the Chinle deposition was occurring, corresponds to the first pulse of the arc. So given this intense volcanic activity and the proximity of the arc to the western end of the Chinle, we expect to see volcanic ashfall zircons along with detrital zircons in the depositional layers. So this research project involves extracting the zircons from the samples that were collected from the western Chinle and for isotopic dating. Based on this information, we'll be able to determine the ages of the different layers and also correlate them with the stratigraphic sequences of Arizona and Utah. Additionally, we'll be able to reconstruct the paleo drainage systems and interpret the Mesozoic tectonic history. Next slide, please. Going back to the subduction zone, this is a characteristic of active plate margins. So you see the subducting oceanic plate going down through the trench. When it reaches a depth of approximately 150 kilometers, hydration melting releases magma, and this magma rises toward the surface, producing these volcanic arcs. As the magma rises through the conduits, large amounts of ash are exuded through the volcanic vent. This ash, along with the zircons that it contains, settles to the ground and gets incorporated into the rock. Dating of these ash zircons dates the rock that it is contained in. The detrital zircons, on the other hand, they come from pre-existing rock that gets eroded and the sediment gets transported by the river systems to the depositional site. And dating these detrital zircons tells us where it came from and allows us to reconstruct the ancient river channels. Next slide, please. So we started processing these samples by first soaking them in a muriatic acid solution that was diluted with 3 parts of water and decanting them. And then we used the standard US sieve size number 60 to separate the sediment grains that were 1/16 millimeters in size or less. Next, we panned these fine grains to remove the lighter sediment. Next, please. The next step involved magnetic separation of these fine grains to remove the ferromagnetic grains and those with iron inclusions. At the end of this step, we were left with predominantly quartz, plagioclase, feldspars, and zircons. The last step involved heavy liquid separation using methylene iodide, which has a density of 3.2 grams per cc. We poured the samples into the solution, and zircons have a density of 4.7 grams per cc, and so they tend to sink through the solution, while the lighter grains like the quartz and feldspars, they float on top. Once we collected the zircons from the bottom of the solution, we washed them in acetone and dried them. This is an image of the zircons that we separated, as seen under a petrographic microscope. Right now, our zircons are at University of Arizona being prepared for laser ablation inductively coupled plasma mass spectrometry. We will be traveling to Arizona later this week to do the isotopic dating, and we hope by the end of this week we'll have images of our zircons similar to this example that you see here. Next slide, please. In 2008, Dickinson and Garrels analyzed a large sample of zircons from Utah, Arizona, Colorado, New Mexico, and Texas. Based on the isotopic data from this analysis, they determined 3 paleo river systems originating in the Wachitas. The lowermost paleo river, or the lower Chinle trunk, receives tributaries from the magmatic arc. Given the location of our samples, we expect to see Triassic age arc-derived zircons in our sample, along with older Yavapai Mazatzal basement zircons, and possibly some from the Wachitas. Next slide, please. Based on the analysis that we are we're scheduled to do later this week, we hope to be able to construct a graph similar to this, where the x-axis shows you the geologic time or age in millions of years, and with multiple spikes that indicate the zircon ages in the population, in the sample. Thank you so much for listening.